Sure. So for the next part of our webinar today, we'll have 3 different presentations from 3 different NSF funded projects that are focused on aspects of Arctic pack ice and landfast ice. And I believe we'll start out with a presentation by Amanda Lynch from Brown University. Amanda, if you're all set to start screen sharing. Thank you so much.
Let's see if I can get this to work the way that it worked before. And
yeah, looks good.
So everyone can see Uummannaq Bay in West Greenland?
Looks great.
Yes.
Okay, great, thanks. So, so I'm representing, actually, let's go back one. I'm representing a project. The PI is Johnny Ryan. He's actually a postdoc here at the Institute. He's out in Greenland at the moment doing our first tranche of field work, and so I'm giving the presentation on Johnny's behalf. So this is a collaboration between a group of us at Brown University, myself, Johnny Ryan, Sarah Cooley, Chris Horvat, and a group at, pardon me, Nordland University, Nordland Research Institute in Beaufort in Norway, Brickdale, who's an anthropologist, Siri Valland, who's a human geographer, and Larry Smith at UCLA, and also Nick Cuba's involved. He was here at Brown, is now at Clark University. And so this was a project that we pulled together last summer, and we're just now getting it off the ground. And as I said, Johnny's just starting his the first field work. So our focus in this project is on Uummannaq Bay in West Greenland. This is an image from April 2017. The pink dots show the 8 settlements in the bay. The population of the bay is around 2,300 people. And the problem that interested us is trying to understand and better characterise the shorefast ice formation and breakup in this region. Every year, stable shorefast ice forms, which provides the local people with a platform for accessing hunting grounds and for travelling between communities. So the shorefast ice has considerable socioeconomic, cultural and ecological significance for the community. However, it remains a significant challenge from the point of view of remote sensing and modelling to provide timely information. And so Johnny, when he was up in Uummannaq doing field work, was discussing this with members of the local community. And through that initial set of discussions, we developed this project. The additional layer on top of this, of course, with all things Arctic, is that climate change is a significant threat to traditional Arctic activities, particularly to safety in the near term, which is something that is a critical issue. And then in the longer term, it may render many of the traditional activities and also the fundamental connectivity between the towns in this area impossible for much of the year. So the first step in this project was to see what we could do remotely. And so we were seeking to document the timing of shorefast ice breakup using daily MODIS satellite imagery, and you can see here a set of images around the town of Uummannaq with land, water and ice classifications. And from that set of images, we can develop a timing of the breakup. And I apologise for the quality I blew it up so that it would be easier to see, but it's a bit fuzzy. So what you can see here is the MODIS time series supplemented with some additional sentinel images that shows the percentage of water in May and then going into freeze up in going through into to melt in June. Sorry, I flipped my hemispheres there for a second. And so what we can do based on those detections of open water is to ascribe a breakup date with a certain degree of uncertainty, depending on the both the resolution of the imagery and also the frequency of the imagery. And so based on this kind of procedure, we can determine the average date of shorefast ice breakup. And so this shows the average date from between 2000 and 2018. The red dots on this image. Can people see my pointer?
Yes. Yes.
Okay, great. So you can see the villages here are shown in red. So here's Uummannaq. And so what we can see is that the earlier breakup is in the southern part of the bay, and we have later breakup as late as after July 1st in the northern part of the bay, and also in the kind of the deep reaches of the fjords there. And so we're able to develop these kinds of maps which let us know about the spatial distribution of breakup across the entire region. The other thing that we can do is look at how breakup is happening at each of the individual villages, just by looking at the pixel that's closest to that village. And when we do that, we can get a time series. So we've listed here all 8 villages and the pixel that's closest to each of those villages in the MODIS imagery. And so what you can see is that we have broadly similar patterns. We have considerable interannual variation, several weeks up to a month in some years. And then there are some years where the shorefast ice didn't form at all. And so if you see here in 2011 and then again in 2005, shorefast ice didn't form at all around Uummannaq itself. And so that's why those are missing. And you can see some other missing data points as well. And that's simply because the ice wasn't there to begin with. So we can see we have considerable variability, both in time and in space, but there's a fair amount of granularity that we're not able to capture based on MODIS alone. And so looking then at Sentinel-2 data, this is from May 13th, 2017, we can get an even closer look. So here's Uummannaq again on the southern tip of the island. If we track the ice over a period of time, what we can see then is the breakup around Uummannaq. So here's an image from 10 days later. We've got clear fracturing around the southern edge of the island. And then by the 30th of May, we have even more fracturing. Now, the issue is that this is a period of at least 17 days where the ice appears to be too fractured to be able to travel on sled, but not enough open water to be able to use boats. And so we wanted to explore with the community about, what this period means for them, how they cope with the variability, both in the timing and then how much time it takes in any given year, and what kinds of approaches they use to determine when and where the ice is safe. And so what we realised through that preliminary work, of course, is that remote sensing is not enough. We need to understand what drives the breakup each year, what are the contributions of warming air and ocean temperatures, and how is that influencing the trajectory of breakup. How does the average breakup date compare to time periods before remote sensing? Was the very early breakup observed in 2016 unprecedented in the memory of the community? Obviously, how will the shorefast ice respond to climate change, and over what timescales? And then how do these changes impact the livelihoods, the hazard management and the development opportunities of the local community? And so this spring then in Uummannaq Bay, Johnny and Britt and Sarah and Chris are all there right now working with the community. They're collecting shorefast ice measurements as part of the whole kind of ground truthing, getting physical measurements of ice thickness and extent to supplement the remote sensing, but more importantly, exchanging knowledge with through interviews and workshops to define the research questions that are going to be important to people at multiple levels. So understanding the research questions that are going to affect locals, that are going to affect policymakers in terms of resourcing issues for this community, and then also what we can contribute to science knowledge in terms of this process. And so what this kind of knowledge co-production process ensures that we study topics that are salient and timely for the decisions that the community is facing. And as I said, we have a particular focus on safety on the ice, but it also opens the possibility of discovering links and connections between the systems that we might otherwise have missed. One of the key things that they're setting up right now is working with the children's home in Uummannaq and other members of the community with simple drone technology to do community monitoring to be ongoing while we're during the time periods where we're not there, which is obviously most of the time. So so we have a group of kids and some other interested individuals who are being trained on the drones and how and when to deploy them. And so they can institute a community monitoring that we can also use to work with our remote sensing data. So that's a quick tour of what we have in mind. We're right at the beginning of this 3-year project, and we're really excited. It's an incredible team that we've got together with a lot of diverse skills and diverse geographies, and the community members have been wonderfully welcoming and enthusiastic about the potential for this technology, both to help with safety, but also to provide educational opportunities. So I'll stop there.
Thanks, Amanda. I think we have some time for a couple of questions, if anyone has some questions for Amanda.
Hey, Amanda, it's Jackie. How are you?
I'm good. How are you, Jackie? Can we have one of your buoys, please?
Pardon?
Can we have one of your buoys, please?
Oh, cool. Question that I had for you, you showed the time series with regard to the breakup dates as you defined remotely. Have you compared those to kind of the local definition of breakup?
So that's what Britt Dahl, who's the anthropologist from Nordland, is one of the questions that he's going to be asking while he's there. And they got there last week, and they're going to be there for the next few weeks to see if we can elicit some memories about when breakup happened in each of the communities. So we'll see how good people's memories are. Another way you can do it is actually when people are prepared to share their photographs, you can often see it there as well.
Cool. That'll be a neat comparison. Thanks.
Yeah.
I have a question, Amanda, for those community observations from the monitoring that they're doing. Are they willing to share that publicly, or do they want to keep those within the community itself?
So they are willing to share it publicly because they consider this to be primarily for them, or the way that we've been thinking about it is very much an educational opportunity. What we've discussed with them so far is that we're very keen to share both the methodology and the products of this this kind of community monitoring, because we think that, you know, kids love drones, and it's something that we could take further to other communities. And so at this point, they're really happy to share this information. That's what they've said to us so far.
Great.
Certainly we offered confidentiality agreements, and they said they didn't need them.
If you do have a public web interface at some point, I hope you will share that with the group. It would be really interesting.
Yeah, we will be doing that.
Fantastic. Thank you. Any other questions for Amanda? All right. We'll have time at the end too to have a group discussion. So thanks, Amanda. I think we'll move on to our next presentation with Jenny Hutchings at Oregon State University. And Jenny, if you have any issues starting screen sharing, please let us know. But she will be doing a presentation on improving models of ice drift and deformations on the ice-coast interaction. Oh, and an updated title. So, Jenny, please go ahead.
Thank you, and thank you for inviting me to talk. I'll try and keep this to the main points of that we found. So this is work that has predominantly been funded by NASA, but is inspiring our NSF modeling project and providing the case studies and boundary conditions that we'll be using in the modeling study. The modeling results are going to be presented in Winnipeg as a poster, so I didn't want to preempt myself because they're not quite ready yet, but I will go over the case studies and the interesting physics with the observational study. And this is work that's recently been accepted at JGR Oceans, and Ben Lewis, my master's student, did all of the hard work here. So many, many years ago, I was inspired by a set of images that Lou Shapiro showed me. These are AVHR images of the Beaufort Sea. Point Barrow is right here. Banks Island right here. And they're only a few days apart, and as you can see, there's a lead that's opening up around here. And next day, the lead is opening here, and this one is closing or refreezing over. And then a few hours later, you see the shore lead open. And Lou refers to these as jump leads. And I've always been intrigued as to what was causing this, because why wouldn't you see leads forming all the way across the shore? Why at these particular points? And Lou Shapiro had spent a lot of time classifying different lead patterns in the Beaufort Sea. And so we extended that work, and Ben Lewis actually built upon that classification to build a table of when each of these leads was open and acting from an AVHR data set between 1993 to 2013. And that data is all published in the paper, so you don't have to spend 6 months doing this work like Ben did. You can get that table from the supplemental material in the paper. So going into a little more detail, what we have found is, and Lou basically was classifying leads in the Beaufort according to their shape and location. And the shape of the lead pattern is basically whether it's curving or linear. And that is directly related to how the mode of failure that's occurring when that lead is forming. Further from that, we looked at ECMWF era interim wind patterns and sea level pressure, and we're able to identify that each one of these lead patterns that we classify is associated with a particular location of a weather system, and occasionally the speed of that travel from west to east or east to west can impact which leads will form. So you can see different lead patterns. This is a classic arch. It's the best example that we have in the record. These are called tangent leads. They form when there's shear. If you remember the few years back, the cracks of doom, that was a blog that formed. That was a particular example of tangent leads that persisted for a long time. And the reason is because there was a high pressure system right up here, actually up here. The jump leads sometimes form a wide angle lead. That's a linear lead that opens up from Richards Island right here. And then you can see more high angle leads forming from Herschel Island. The main point here is that the leads only emanate from 4 promontories along the Beaufort coast. And these are the leads that emanate and go straight into the Beaufort Sea. Let's go back. So you can see ones here, and you can see these ones here. Between those promontories, we find that the minimum landfast ice extent is typically smooth between the promontories. And this is the landfast ice extent was provided to me by Andy Mahoney. And it's typically the boundary condition that's important is the one that is the minimum extent according to his definition, which is basically the grounded landfast ice and the ice that persists throughout the middle of winter. So I'm not going to go into too much detail here because I only have 10 minutes, but basically what we did was we looked at where high pressure systems and low pressure systems were falling by contouring sea level pressure, mean sea level pressure. We looked at the wind fields, which is the red arrows on here from ECMWF. We looked at ice drift from the National Snow and Ice Data Center ice drift product that was provided by Mark Schutte and Chuck Fowler. And actually what's really nice is how well this passive microwave ice drift product, essentially passive microwave, it also uses the AVHR imagery, aligns with what you would expect the drift pattern to be based on the leads location. So this here in panel A is basically a shear failure where the ice is moving around like this, and the ice drift is confined by that lead. We see the same thing in the example of the arch, and when you have the howls, which are emanating around Herschel Island forming, the ice drift is concentrated on the leeward side of that lead. There are quite a few different definitions of lead patterns. I'm actually only going to focus on the ones that emanate from the coast in this talk because they're interesting in that they are driven by a high pressure system, and therefore they are a major contributor to the Beaufort gyre motion in winter. And if we go back to Lou Shapiro's example, basically what was happening here was you have a high pressure system that's centered on where these cracks terminate, and it was moving from west to east. And we see this happening over and over again throughout the data set, and depending on where that high pressure system moves depends on which leads form and when they form. And sometimes the high pressure system will go across the Beaufort like this, and sometimes it will go down into the Mackenzie Basin like this, and you will see different crack patterns occurring which way that weather system goes. So this basically tells us that if we want to model this opening, we need to have a model that, one, can reproduce the cracks and leads opening, and 2, has the correct boundary condition, and 3, has a reasonable representation of where the anticyclones are and their speed of traverse across the ocean. So that is what we're going to be trying to do in our modeling experiment, and we're going to be using a discrete element method model for that. So just a little bit on some interesting points about these lead patterns. One thing is they have seasonality. Each one of these panels is a different classification of pattern, and the main point in the details here that there's not enough time to go through is basically that the seasonality of these patterns generally follows the location of the weather systems, which is not surprising. So the Beaufort High has a seasonality where in December it tends to be in the west, and in May it tends to be in the east. And which lead patterns are activated follows that seasonality. There was one exception to this. This is a particular lead pattern which is intersecting angles of leads that's formed under compression, and that has it increases the seasonality of that pattern actually is such that it increases in early winter and late May, so around about just before the start of breakup. So that is probably related to changes in the compressive strength of the ice. So that's the only exception. We didn't see any trends in the leads that we classified as to whether they were becoming more prominent or more of them were happening in recent years. Maybe this is surprising because we keep talking about ice becoming weaker and ice drift increasing, but actually in winter, the ice drift is not increasing dramatically in the Beaufort Sea. And because all of these fractures form in tension and ice is typically weak to tension, it's actually not so surprising that we're not seeing an increase in the rate of these leads opening. There is no minimum threshold for the wind along the Beaufort Sea coast, so the easterlies, that is causing these cracks to open. They'll open under any wind speed. So it is literally the location of the weather systems that's controlling when they open. We did a very simplistic analysis of drift across gates. These gates are the dotted lines on this figure, and the location of them was chosen based on where they fell relative to particular fracture patterns. So I'm showing that in this image, that you have a arch that forms off Point Barrow here. You've got another one here. The green gate, the flux across that was representing motion from the Barrow arch, which is this one. And then you have another gate that represents motion across into the East Siberian Sea, or the red gate down into the Chukchi Sea, and so on throughout this. And the drift product we used, again, was that National Snow and Ice Data drift product, because it so nicely delineates the drift across the fractures. So we didn't want to look at drift associated with particular fractures. We wanted to look at this in a statistical sense across all of the fractures that occurred. And so we classify coastal leads as leads that are opening when there's anticyclonic wind forcing, and we look at only the leads that emanate from the coast and propagate through, they're propagating actually quite far into the Beaufort Sea, up to about 500 miles. And of the days when we have clear imagery, the coastal leads were active on 38% of clear days. And we find that motion into the Chukchi was for 94% of the motion was explained by that 38% on clear days. And for each one of these gates, we have a higher percentage of the ice drift explained on the days when the coastal leads were open than in between. The decreasing correlation as you go further east is likely to do with the fact that you have the coastal shear zone acting occasionally, and we're not capturing that in this data set, which is also driven by anticyclonic weather conditions. But this still gives me confidence that it's actually very important to model these features if we want to get the correct Beaufort gyre motion in winter. And the one thing that I would like to point out is the seasonality of this Beaufort gyre motion, where you have an increase in coastal leads emanating from Point Barrow in December, and then the coastal floor lead system being activated in May, more typically, means that during winter, it's actually quite unlikely for us to get ice from the north of Prince Patrick Island here and the north of the Canadian archipelago round into the Beaufort Gyre. And this explains why, likely explains why in recent years we have seen that the tongue of ice in the Beaufort Sea has not actually really been here for many years, because that ice simply hasn't been moved around the Beaufort Gyre. So you don't have the multi-year ice in place here unless you are able to move it. And then what happens is in summer, any ice that's in this region is melting out nowadays. So there's an interesting story in here that we would like to get out with modeling. So we need to improve our models. So the job for us is to improve the boundary condition, which requires landfast ice. As a first step, we'll be putting that in as a fixed boundary condition, but I'm really interested in any work out there that's going to be improving our landfast ice models. And we need to get the response of the ice to be able to crack with the correct weather system and with the weather systems in the correct place. And we have had some good initial results with that, which I'm not showing here because they're quite messy, but the first result that we do have is that you absolutely need to have the landfast ice boundary in order to get the cracking in the right place. Otherwise, you'll get cracking all over the Beaufort Sea when you expect to only get an arch like this. And in order for an arch like this to form, you need to have the wind blowing against Point Barrow so that the, so that the ice failure is actually being initiated at this point, and then the crack propagates through the pack. So thank you very much for your attention. Sorry if I overran. I'll let you read the findings here.
Thanks, Jenny. Does anyone have a quick question for Jenny?
Hi, it's Martin. Hi, Jenny.
Hi.
I wondered if you've spoken with Lynn McNutt about your work, because she did a lot of work on fracture patterns in the Beaufort Sea many years ago. And I think some of that informed Lou Shapiro's thinking and activities.
Yeah, actually, Lynn McNutt's paper with Jim Overland on hierarchy and in the ice dynamics was pretty much inspirational for trying to get at this question of what's the role of the boundary conditions. I have talked to her, but she's not really interested in sea ice dynamics anymore. She's working in radio. Thank you.
Great. I think we might follow up with Jenny at the end if we have any more time, and we will move on to our last presentation today. And John, feel free to start sharing your screen. John Toole from WHOI. And I might refrain from introducing his topic because it may have been an update.
Jenny, if you will click the stop share button, and then John will be able to share his screen.
Sorry, I've got to find. There we go. Sorry about that.
No worries. Thank you.
Okay.
Here.
Great.
So hi, everyone. I was asked to give you an overview of our AON program making sustained measurements of the Arctic Ocean, actually below the sea ice. But of course, the ice itself and the ocean are intimately related. You know, melting ice changes the salinity of the ocean. Ocean heat content can change the ice, melt the ice. And so you really can't separate the ice from the ocean in the Arctic. So this AON project is a cast of many, and I just wanted to give a shout out to many of the named people here that are playing intimate roles in the field program and also the interpretation and analysis of the data. But I also make note of the countless engineers and technicians that are helping us out in the field to deploy instrumentation. Particular kudos go to Rick Krishfield, my long-term collaborator in this project. So I'm sure most of you are familiar with the International Argo Float Program. This team of investigators worldwide are presently maintaining roughly 4,000 of these little robots that are sampling the temperate and tropical oceans every 10 days. So the Argo float is ballasted typically to be neutrally buoyant at about 1,000 meters depth. And typically they're programmed to sink down to that depth and drift with the ocean currents for 9 days. And then on the 10th day, by changing their volume, they actually make themselves buoyant and they rise up through the water column, carrying sensors that measure the water properties as they go. And when they get to the surface, they find out where they are with a GPS receiver, and then they send their position and their observations of water properties through satellite back to shoreside users. Now, this is not a particularly great map projection for this next point, but you'll notice that there are very few dots, very few floats operating in the high northern latitudes. And of course, there's a good reason for that, in that in the Arctic, over much of the year, there's a hard ceiling to the Arctic Ocean. And these standard Argo floats need to actually come to the surface to figure out where they are and to send their data home. And when you have a hard ceiling, the floats have difficulty doing that. So about, say, 15 years ago, we started to develop technology to try and become Argo of the Arctic. That is, an instrumentation that could sample the Arctic Ocean 24/7, 365 days a year. And the device we ended up with has a surface buoy that sits on the ice, supporting a wire rope tether extending down up to 800 meters depth. And then the heart of the system is this little vehicle that is in size and shape much like an Argo float that crawls up and down the wire carrying sensors that, again, sample the water properties. The data are sent up to the surface unit and then home through satellite. And our vision for this project is much like Argo, is to maintain an incoherent array throughout the deep Arctic Ocean, sending back data in real time that anyone can actually access and do science with. The program began with a first deployment in 2004, and through the support from the National Science Foundation, Office of Naval Research, and various other collaborators around the world, collectively we've deployed about 100 of these systems in the Arctic, and collectively they've returned something like 80,000 temperature and salinity profiles from the deep ocean. So the standard instrument carries a CTD that measures data from which we can get temperature and salinity as a function of depth. It's pretty easy to add dissolved oxygen to that CTD sensor. With Navy support, we've deployed a few ITPs with a velocity sensor on them. So with these ITP-Vs, we collect temperature and salinity and ocean velocity profile data with depth, and we also can sample the turbulent characteristics in the mixed layer underneath this ice-ocean interface. Sam Laney has developed a bio-optical package that has gone on some of our ITPs. I'll say a little bit more about this instrument at the end of my talk. So these are all instruments that actually fit on the vehicle and crawl up and down the wire. We also have the capability of supporting instruments on the tether, either above or below the profiling segment. And one such device is the SAMI sensors that Michael de Grandpré at the University of Montana develops. These measure either CO2 concentration or water pH. And the data from Mike's SAMI sensors go through our same network and are acquired by us. Now, when we first started the program, the Arctic sea ice was nice and robust and thick and happy. And over time, we all know that the ice is getting thinner and more mobile. And so what we've had to adapt, like any good organism on Earth. And so what we've done now is make the ITP system amphibious. And so we've actually deployed about a half a dozen systems in open water in leads between the ice. And the vast majority of those have actually survived fall freeze up and then carried on. So that's the technology. And as I said, we've deployed about 100 of these things collectively over the last 15 years. This next figure shows how we're actually doing. The top panel shows a histogram of how many days of ocean observations we're getting from our collection of ITP systems. So the x-axis here is in profile or days, and these are the number of ITP systems on the y-axis. And you can see we've had a few heroes here of ITP systems that have lasted more than 2 years. We've had also an uncomfortable number that die quite early. But on average, an ITP system will return ocean observations for roughly a year. The lower part of this figure shows the performance of each individual system over time. As I said, we've deployed about 100 of these things. The black bars mark the time interval over which we've obtained subsurface ocean observation from the instrument. And the gray bar extension is the time interval over which we've continued to collect position information. So these ITP surface packages record GPS fixes every hour or half an hour. And those data are recovered daily. And people that are using and developing sea ice drift models are using these data to sort of validate some of their model predictions. So as I said, we've been in this business since 2004 and collectively collected something like 80,000 temperature and salinity profiles from about 100 instruments. And in yellow here is shown the distribution of temperature and salinity profiles that we've collected from these systems, these little robots. They look like continuous lines, but in fact they're made up, at this resolution, they look like continuous lines, but they're actually individual dots. We're typically collecting 2 or more profiles a day, and with a typical ice drift of 10 centimeters a second, we're getting quite superb horizontal resolution, sort of unprecedented compared to any other technology. In red are marked the locations of ship or aircraft observations over the same 15-year time period. And collectively, there have been about 19,000 of those over this interval. So at first glance, you'd say, wow, ITPs are doing a great job compared to manned operations. But if you look at the map, you can see that the data set's really quite complementary. The ship observations and the manned observations tend to be acquired around the periphery of the Arctic, and the deep ocean is sampled by these ITPs. And so collectively, which we encourage people to use the collected data set, you have pretty good spatial coverage over most of the Arctic. So that's the technology, and as I said early at the outset, it's very much a intensive and collaborative effort. Here are some of the ships and aircrafts we've been using to deploy these instruments. We basically piggyback on ships of opportunity and are always interested in learning about opportunities to get our instruments out in the field. And in my remaining time, I just want to give you a sense of some of the science that's being done with these data. So early on, Ben Robbie took the lead and looking at decadal changes in upper ocean salinity in the Arctic. It was quantified in terms of the freshwater content. And you can think about freshwater content as the amount of fresh water you have to add to an ocean of say a constant reference salinity of 35 in order to get the observed salinities. So Ben took available ship observations and aircraft observations from the 1990s and constructed this map of upper ocean freshwater content, where blue marks low freshwater content relative to the reference salinity, and this purple and reddish colors are high freshwater content. And as we all know, the Canada Basin, the Beaufort Gyre, is a big reservoir of fresh water compared to the inflowing North Atlantic waters. He did the same analysis with data from the International Polar Year 2007-8. And you can see, again, the data locations. The ITPs are these darker squiggles because they have many more observations in time. To first order, the pattern looks very similar, but you can see the pattern is actually more intense during the IPY than the 1990s. And this right panel shows the difference plot, where reds indicate something like 4 or more meters of excess fresh water in the upper ocean compared to the 1990s. And so work since has been focused on trying to understand the source of this extra fresh water, how much of it comes from ice melt, how much of it comes from river input from North America and from Siberia. And that's a current ongoing research topic. As I said, ITPs sample 24/7, 365, and so they're very good at investigating annual variability. And for reference here are late winter and late summer temperature, salinity, and density profiles of the upper 300 meters from a location in the central Canada Basin that happened to be sampled by the same ITP that sort of did a little circuit over 6 months and came back to basically the same point. So down here at 300 meters, we have the temperature maximum of the Atlantic water. The ITP data actually go to 750 meters, but I'm only showing the upper 300. So you don't actually see that the actual maximum Atlantic water temperature. Moving up, we see the Pacific winter water layer. And continuing still farther up, we see a very warm subsurface intrusion. This is the Pacific summer water. This is the Pacific winter water, Pacific summer water. And then in winter, we typically see a pretty well-mixed surface layer. In this case, roughly 40 meters thick. But that's a depth interval that is dramatically changed in summer, where with chiefly from ice melt, local ice melt, the surface waters get significantly fresher. So there's a nice large salinity gradient through this layer that was homogenized in winter. And within that salinity gradient, there's this so-called near surface temperature maximum layer. And what's of interest is that this shallow temperature maximum layer is in the depth span that's homogenized in winter. And so all this heat that's being stored in summer in this near surface temperature layer gets vented up to the surface and probably affects the development of sea ice the next winter. So Ben Raby did his paper on interannual variations of freshwater, but you can do similar kinds of calculations with heat content. And just for reference, here's a comparison to late winter and late summer profiles of temperature, salinity, and density in the same general area of the Canada Basin from 1975 from the AJAX experiment. So here's the Atlantic water layer temperature maximum. That's a little bit warmer now than it was back in 75. There's the Pacific winter water layer. And we move up still shallower. The Pacific summer water layer is really muted in comparison to what it is of late, as you can see. And this near surface temperature maximum layer is only very hinted at in 1975.
Hey, John, we're at the top of our hour. If you wouldn't mind just wrapping up.
All right, so there's lots of science projects. This is the paper that Mary Louise Timmermans led, looking at the recent evolution of Pacific summer water heat. And you can see it's really going up dramatically. And there's enough heat there to melt about 50 centimeters of ice if you could mix it up to the surface. So I call this sort of a time bomb. This heat is down in the ocean and it's going to eventually affect the surface somehow. This is the biology sensor that Sam Laney put together, looking at, say, in this case, looking at chlorophyll fluorescence and summertime blooms. So just to wrap up quickly, thanks to the support from the AON program and also ONR, the ITP program is continuing. 2019 looks like a very busy field season. We'll be deploying instruments in conjunction with Mosaic, in conjunction with this KTEX East and West Acoustics experiment, and also in conjunction with the BJOS program. As I said, all data are immediately updated from the instruments in the field. You can access them from our website, or you can go to the NOAA NCEI website that mirrors us, and metadata are also at the AON website. So I'll end with that. Sorry for running long.